Hi all. In this video we will assume that we're near the surface of the Earth and that the acceleration due to gravity is constant. So let's remember that the acceleration of an object is how much the magnitude of the velocity is changing and in what direction it changes. So let's say that we start off with a ball that will have initially a zero velocity and it's going to fall downwards at a rate with acceleration due to gravity of g. So what we can say is by looking at this, that acceleration is how much the velocity changes and in what direction. The velocity is going to be increasing downwards because the ball is going to fall downwards, and as time goes on it's going to get larger in magnitude, the velocity that is. Acceleration has units of meters per second squared. If we multiply it by seconds, we'll end up with meters per second, which are the units of velocity. So our v as a function of time is going to be just gravity times time. So what this is saying is at time zero, we have zero velocity, and as time moves forward, our velocity gets larger and larger. So we can graph a couple things right now. We can graph the acceleration versus time. So acceleration, time, and it should be some constant value which corresponds to g. We can also graph our velocity as a function of time. So we start off at zero, so we have to start down here, and then we just move up linearly. So this is linear in time because it's only t to the 1, and then the slope of this line is equal to g. There's a couple other things that we can point out. For instance, the amount of area underneath the acceleration curve, this, is a measure of how much velocity we've gained. So this area here at this time, say t1, would correspond to the velocity here at a time t1. Likewise, if we looked at the amount of area underneath this curve here, this is the amount of distance we've accumulated. So we can remember that distance is equal to velocity times time. That's the average velocity. So what we need to do is we need to get a meters per second multiplied by a second so that we end up with meters. So in here we kind of lucked out because our acceleration was constant. So if we multiplied our acceleration times time, we get this full area because it's a rectangle. But over here we have a triangle. So if we were to multiply t1 times this velocity here, then we'd get the total, we'd get this area here, and we'd be getting the area of a rectangle and not a triangle. So what we need to do is multiply our velocity times time. This is for distance. So we get our velocity times time, and since it's a triangle, multiply it by 1/2. So this ends up being 1/2 gt squared. So our position as a function of time graph will be a parabola. And then there's a couple other things we can see here. So the velocity will be equal to the slope tangent to a point. So this is the velocity at this point here. So what you can see is over here, it starts off with 0 velocity because the slope is equal to 0 and the velocity keeps increasing. And this right here, so the fact that this is sort of like half a smiley face means it is concave up, so that means that it's accelerating. If it was more of a frowny face, so something like this, it would be decelerating. But the velocity could also be positive, or the velocity is positive, since tangent is positive and over here it'd be 0. All right, thank you very much.